Greetings, Panthers. Dr. Augustine. In our first video about precipitation reactions, we talked about solubility rules and just the general idea of a precipitation reaction. We use this reaction as our base, forming lead iodides. This is sort of the classic golden rain reaction. We take two clear solutions, we dump them together, and they make this beautiful yellow-colored solution. And we talked about the solubility rules to determine which of the products are actually going to form solids and which ones aren't. And then the other thing we talked about was the fact that this was an exchange reaction. We were going to take the cation from one and react with the anion from the other and exchange cations and anions, and then we go and look in the solubility tables to see which one's going to be solid, which one's not going to be solid. And from there, we can figure out what the chemical reaction should be. So this is called the molecular equation. This is the balanced equation of the chemical reaction that has taken place. And today we're going to talk about two other ways to express this, and they have different reasons for writing these different ways. So let's take this molecular equation and let's actually break it down. And the first thing, the important thing to recognize is whenever you see an AQ, that really means that it's a solution of these ions. They're not actually attached together. They are surrounded by water molecules, just like these two pictures show right here. So for these two reactants, potassium iodide and lead nitrate, they're not actually attached to each other. So perhaps a better way to write this reaction would be to break apart the ion. So it's really a K plus ion in aqueous solution plus an iodide ion in aqueous solution. Now, what do we do with this 2? The 2 has to be distributed to both species. So there's actually 2 K plus ions and 2 I minus ions for every one of these potassium iodides in the balanced equation. Then, this is aqueous, so this one also needs to be broken up. So it's going to be Pb2 plus aqueous plus, there's a little 2 down here. That means there's actually 2 nitrates, 2 NO3 minus aqueous. Okay, that takes care of the reactant side of the equation. What about the product side of the equation? So the product side of the equation is PbI2, and notice that one's a solid, so we don't break that one apart. So it's PbI2, lead iodide, and that one is a solid. We leave it together, but we've got this one as an aqueous, so we need to break that apart again. 2K plus aqueous plus 2 NO3 minus aqueous. Okay, this version of writing this equation is called the complete ionic equation. At least that's what Tro calls it, and quite a few books call it something like that. Complete ionic equation. So this is the overall ionic equation, and really this is showing you much more accurately what's happening at the solution scale. So if you were looking in the solution, like for instance this right here, you would see we have K plus ions, iodide ions, lead 2 plus ions, nitrate ions. Then when we react them together, we end up with lead iodide as a solid. That's what's shown in this picture, plus K plus ions and nitrate ions. That's shown in this picture. Okay, that's called the complete ionic equation. So if you look at this carefully and you think of this arrow as being like an equal sign, so in math, you know if you have the same things on both sides, the arrow right here, we can think of this as being like an equal sign. So if you look on here, you notice on this side of the reaction, we've got a bunch of species. On this side, we've got a bunch of species. And what you'll notice is we have some of the same species. This 2K plus occurs on both sides of the species. The 2 NO3 minus occurs on both sides of the species, both sides of the reaction. So those are the spectator ions, and we can cross them off and write a new type of reaction. Okay, so these are the spectator ions that I'm crossing off. So let's rewrite this equation without the spectator ions present. Pb2 plus 2I minus yields PbI2, and that's a solid. And we've got the correct states of matter on here, And now we recognize this is a new form of equation, a much simpler equation, much less going on. That's actually showing what's happening in the chemical reaction without the spectator ions. We call this one the net ionic equation. Okay, so 3 different equations. Molecular equation is the one you're most familiar with. Complete ionic equation is when you actually break the ions apart. When do you break the ions apart? Whenever you see an AQ. That's actually implying that the ions are broken apart. And then the third one is called the net ionic equation. And that is just the reactants that are doing something and the products that are being formed. We ignore the spectator ions for the net ionic equation. A couple of important points before I wrap this one up. When you write the molecular equation and you have some coefficients out in front, for example, this 2Ki, remember you need to distribute those to both species, 2K plus, 2I minus. There's actually 2 potassium ions and 2 iodide ions. Likewise, if you have a subscript for a polyatomic ion, 2 nitrates, you need to bring that out in front. That's actually 2 nitrates that are being represented with this reaction. And then, of course, we need to include the states of matter. Aqueous for these, solid for these. How do we figure those out? That goes back to the solubility rules.